So I am going to talk about the MSA planning tool, and this is what Torsten was referring to as the smarts, hopefully, behind planning for your MSA observations. And I'll explain why we need a tool like this. My name is Diane Karakla. I'm with Space Telescope Science Institute and the NIRSpec team there. Okay, so just a few slides about some general words about observing considerations with, for MOS spectroscopy. I just wanted to point out that there is a timeline for MSA observations, and I think Torsten gave a good description about why you would need to possibly have a two-phase approach, which is what we're anticipating for most of our MOS observations. Because of the accuracy needed to, on the positioning, we expect that most people will want to do near-cam pre-imaging. So this is one of the elements of the timeline here. So there are going to be two proposal or submission phases. There's a proposal submission phase and a program submission phase with the detailed MSA planning tool products, basically, that will be detailed observations will be here at this phase. So there are two major factors that drive the reason for this two-phase approach. And one of them is to be able to allow scheduling flexibility for MSA observations because of what Jeff had talked about earlier about the instantaneous field of regard of JWST is changing throughout the cycle and only allowing certain orients on at certain times of the cycle. So we would like to be able to schedule those MSA observations ourselves at Space Telescope and then deliver an assigned orient to the observers. So when observations come in, requested observations come in, the TAC process will proceed and then we'll accept certain science programs. And then a long-range plan will be developed, at which point fixed orients are assigned to programs that have been accepted. And then following that, the second factor that's driving, again, this two-phase approach is that what I said before, the need for the near-cam pre-imaging in order to get the associated 5 millisecond relative astrometric positions on both the sources that you're going to find in your near-cam pre-imaging, but also on the reference stars that will be needed to do the MSA TA for your MOS spectroscopy. So program submission will include the details after running the MSA planning tool, but we also ask that you practice using the MSA planning tool because it will be very useful for giving you a sense of the relationship between the number of targets that you can get at each pointing, how well observed through a set of dithers your targets are, and you can explore how your exposure depth parameter changes with the number of targets that you can observe at each pointing. So it's a very useful exercise to start doing now, I think. So this mode of observation is one of our most complicated modes of observing on the telescope. So we do have, unlike all of the other APT templates, we have this tool to assist people to populate the APT template parameters. Okay, I think I went there. So the second slide I wanted to have a general introduction about is again about, I think Torsten said enough about TA. He was talking primarily about this regime here for optimal TA, which allows the best possible photometric accuracy of your sources. And that will help to place positions into the MSA shutters with less than 20 millisecond accuracy. It has to start with a catalog with 5 millisecond accuracy, though. So that is generally possible with near-cam imaging, pre-imaging, as I described. And this is equivalent to about 1/10 of a shutter width. So that's the type of accuracy that's needed for that, for the best possible photometry. But we're also allowing for the relaxed MSA target acquisition strategy using the 5 to 20 reference stars, as this one does, which can deliver a somewhat more relaxed target accuracy, target positioning accuracy, starting with catalog accuracies that are much more flexible, I would say, than this case here. And so it's possible to use existing HST imaging to get into even this bin here, but with a lot of work, I would say, to get into the optimal TA regime. Certainly into this regime, it should be possible with existing imaging, but primarily we're expecting people to want to request NIRCam pre-imaging in their programs. So that would be an observation that you prescribe within your program, your MOS spectroscopy program. You would put an observation for the NIRCam imaging in the same program. The timing of the two observations would be linked so that there would be at least a minimum of 6 weeks, 6 weeks between those observations to allow for processing of the observations and scheduling down on the ground. And I want to say a word about the size of the area, that you should make sure that you have coverage for a minimum, I would say, of 5 arc-minute square in the imaging, whatever imaging that you use, because this will help the MSA planning tool select from a number of different possible pointings, and it will help to find reference stars across the entire MSA. On the last bit here on the table, there is optionally, outside of MSATA with reference stars, there's an option to use verify only, which will, we think, deliver about 1/10 of an arc-second accuracy just from guide star acquisition. And no reference stars are required, no pre-imaging is required for this. So if your science can accept this type of accuracy, then that's also an option that we provide in the template. Okay. So on to describing more of the MSA planning tool, the challenges that an observer would have without a tool to worry about certain things. So first of all, as everyone said, the MSA is a fixed grid. So there are vignetted areas behind the shutter bars where targets will suffer a lot if they fall there in their photometry. So you want to avoid those areas if at all possible. There's also the gap between the detectors that Torsten talked about right here, and it's a 20 arc-second gap. And so dithering, we've already said why you would want to do dithering for a number of different reasons that I've outlined here as well. But the key here is that the MSA planning tool worries about this particular thing. Through the dither set that you prescribe, and I'll describe that a little bit later, it's going to worry about re-observing those same targets at every dither point. This is what is very hard to do by yourself on the ground. And then, okay, let me go to the next part here. So again, this is the real MSA with all of the bad stuck shutters and closed, shorted rows and that sort of thing. So that's really what we're dealing with. The MSA planning tool has to avoid the use of those shutters when it's trying to derive the optimal pointings. Okay, and then let's see. Yeah, and then of course the positioning requires the detailed knowledge of the optical distortions in the fore optics of the not only the telescope but in the instrument fore optics, and velocity aberrations due to the telescope's movement at any given time of the year for any given orient. So MPT worries about all of this stuff for you. It has it all in there. All the smarts are in there for that. Okay, so now these are the parameters. I'm going to start talking about a few of the parameters that you can use in the MSA planning tool to actually help you design your science program, to tweak things for different science cases. So in this particular case, what I'm showing is these are the slit losses as a function of wavelength. So we have a parameter. Excuse me. We have a parameter for shutter margin. I'll talk about this one first. I should have started with that one, but the shutter margin is the ability, it gives you the ability to confine your source centering at tighter and tighter levels inside the MSA, inside of the shutter. And so the constraints allow you to have some control on your slit losses, as you can see. Excuse me, I need water. Sorry. The other parameter that you see is the shape of the slit lid itself. And Torsten talked about a 3-shutter slit, which is pictured here with the target at the center, but we have other choices as well in the MSA planning tool. One word about this: in order to make use of the source centering constraints in the tool, you'll need to be in that optimal TA regime of less than 15 milliarc seconds or so. Okay, so another thing that you can do is you can have, the way MPT works is it ingests a catalog of sources. Excuse me. And the catalog can have target weights associated with each of the targets. And if you do this, if you provide these in the catalog, you can actually use them in the tool to create plans that prefer targets with higher weights than others. So this is just a picture of the planning results pane of APT after MPT is run. Okay, and then another thing that you can do is you can actually shuffle the candidate list. So what we do from the catalog, we ask that the user, excuse me, we ask that the user derive 2 filtered sets of candidates. One is the primary candidate set, the other is the filler candidate set. The primary candidate set is used to basically derive the optimal pointings. Those are the targets that you really, really want to observe. You should put them into the primary candidate set because that's the set that uses target weights. The fillers will be added into an MSA configuration after a pointing is selected based on the primaries. Pointings selected based on the primaries, and then the configurations are built for each pointing. So this is just showing you that you can actually, so if you do your ordering of sources from 1 through 5 in a certain area of the MSA, if you follow a natural ordering like this, then you can really only fit 2 3-shutter slitlets in here cleanly. But if you shuffle the candidate list and then try a different order of sources, you can actually get 3 in there. So it's just showing you that basically this parameter that we have to be able to do Monte Carlo optimization in the planning tool, this is what it does. It actually tries to optimize the configuration once the pointing is already set. Okay, dithering. So there's 2 flavors of dithering in the MSA planning tool. Well, actually 3. There's the in-slit nods that Torsten talked about. So where the target is, reobserved up and down, the telescope is moved by a very small amount up or down in the slit, and so the targets appear in the top or bottom shutter as well as the central shutter. And in that case, you get 3, for the 3-shutter slit, you get 3 exposures. But the same MSA configuration can be used, so you're saving in MSA configurations. And then for fixed or flexible, I wanted to talk about primary dithers next. There's 2 flavors. There's fixed dithers and flexible dithers. What the fixed dithers does is it just translates the pattern of shutters for all of the targets on the MSA. But the limitation with this approach is that you can only use small dithers because the optical distortions that are present at each pointing have to be taken into account. And so a source that's, for example, at the edge of a shutter in dither point number 1 may fall outside of the shutter at dither point number 2. So you can lose sources this way using this particular fixed dither approach. But it's straightforward and it works well for small dithers. For flexible dithers, what the user does is prescribe a set of constraints between primary dither points. And then, so that's like a minimum or a maximum separation between dither points. So this methodology is appropriate for large dithers, and it's used to cross the detector gap, for example, which is about a 20 arc-second move. And then multiple possible pointings are tested at each dither step. So that builds a family of possible solutions. So we start out by looking at, like I said, at a number of different possible pointings for pointing number 1. And based on those pointings and the applied constraints, we derive a whole set of different possibilities for position 2 for each one of those positions in set 1. And so as you can see, it just builds up with the number of dithers that you specify into a large number of possible families. And in the case of MPT, it chooses the best family for you, unlike in real life. So you've got your best family chosen for you. And that's the one that observes the most highly weighted sources at a given pointing. One other thing I just want to mention briefly is that the reference star selection, it could be very daunting, but we've tried to simplify that for people. If you provide a catalog which has some prerequisites in it, which is fluxes in the NIRSpec TA filters, and a column representing whether or not a source can be used as a reference star or not, then the MPT will actually help you choose the reference stars. It will help you choose not only a set of reference stars that are appropriate, but it will choose for you the TA filter and the TA readout pattern that you'll need to specify, and it populates APT with that information. Now, we're going to have a script to help you provide these inputs. That's going to be outside of the MSA planning tool. And the NIRCam pipeline it'll be a script that we include in the NIRCam pipeline as well to derive those things automatically. Okay, for the planning tool inputs, we've already talked about a number of these. As well as with the things I've mentioned before, we're going to have to specify gratings and filters. These are the dithers that I talked about. There will be a set of search grid parameters, which will be, you can use the default set of search grid parameters that are derived based on the area of the catalog that you include, or you can fine-tune it. And then you can select whether to use the source weights or enable the MC shuffling the mix shuffling that I talked about. And then you give it a number of MSA configurations to design based on what's required for your plan. And if you do more than what's required for one plan, what will happen is it will design multiple target sets. It will dig deeper into your primary candidate list and derive extra candidate sets for you, extra sets of targets for you. Okay, and now as far as outputs, the output from a plan, from the MSA planning tool is, as Torsten said, a group of pointings. These are the preferred pointings and the sources that will be observed at those pointings and the MSA configurations that are needed to observe those sources. And then there's a last step when you can run as many plans as you want in practical. Practical limits are probably about 4 or 5 plans. And then you'll want to select one of those plans for your observation and just click a button to create an observation from that. I just want to say one word about practical limits on the software. These are the key parameters that control particularly the memory that's used by APT. So you want this combination of combinations of things to be limited. And I can provide more information about that in one-on-one demos if you'd like to talk to me about that. MPT is still under development, so there's the normal disclaimer that users should not expect that the number of targets that they observe in any given configuration here is going to be the actual number of targets yet. We're still working on the geometrical transformations and a number of other things for our software. Okay, so there's going to be an area to review plan results, and this will include the ability to highlight or select certain exposures. These are the exposures here. It's actually a shortened name for each of the exposures. It's built by adding the configuration number and the exposure number, and that's how you can distinguish between the different pointings. You can select exposures here, and then the results that you see in this area here depend on not only what you selected here for exposures, but how you filtered those exposure results. You can choose targets in at least one exposure to show, or you can choose targets in all exposures to show. And you can choose between different flavors of targets, primary, filler, contaminants, or all. And what you get in the end is just a listing of your results showing the exposures in which you had some success. It also tells you the number of exposures that you got from your selection. And then there's a histogram presenting this information that's here in a slightly different way in terms of numbers of exposures. Okay, I said all of that. We also have the ability in the MSA Planning tool to use the Aladdin viewer to display an image, if you have an image of your field, and then overlay the successful shutters for targets if you decide to do that. You would have to do it for each exposure. This is an exposure basis tool. Also, different exposure views in the tool itself are this MSA shutter view. And it's nice because it instantaneously gives you an idea of how much of the MSA you're utilizing, and to see if you have any extra free rows that you can stick extra observations of targets in, if possible. But it maps the positions of targets onto this MSA array at the MSA plane. And it shows, like I said, the colorized rows. There's red rows showing the rows that you need to avoid for open shutters that are there in the row. But the colors of the targets are green for primaries, blue for fillers, and black for contaminants. We don't have a process for eliminating contaminants for planning around them a priori at this moment, but we're going to think about that a little bit more. This is now what we're calling a collapsed shutter view, which is an alternate view. It's selected by one of these icons. The MSA shutter view is here. And if you click on this instead, you get this view. And this is showing for a virtual shutter. It's showing where all of the targets are. All your primary targets are in green, and filler targets are in blue. So it's the same idea. And it shows you how good you're centering. Oh, the other thing about this is that you can actually highlight one of these dots, and then it gets illuminated over here. So you can kind of correlate the information in different views. OK, I think I need to escape and do the demo at this point. And the beach ball of death here. OK, so this is the APT. For 10 minutes? OK. So this is APT, and generally you start by selecting, I have a beach ball. This is not good. Maybe I should get rid of the APT, the Aladdin view. This was working before, it really was. Moments ago. I don't know what's going on. Okay, this is not going to be good. If I can't select anything. Yeah, if you want to take questions, I'm just trying to click on things here. This is not going to be good if I can't show it. I can't even get PowerPoint back up. Okay. No. What? Restart APT? Okay. I'll try. Let's see. I need to click onto something else, right? Force quit it. Responding even to that. I can't quit. I can't quit. Okay, wow. Okay, great. All right, let's try this again. Okay, so this is the starting place in APT, and you can say new JWST proposal, and you get these 4 things. If you're just playing around, you don't have to worry about red X's. So I'm just going to click on observations, go to a new observation folder. And now from the this is the level at which you describe your MSA, you do your MSA plans from this level. You have to click over into the MSA planning tool to get out of the template mode. Okay, so the first thing you want to do, these are laid out in order. You have to define a catalog first and ingest it, and then you select your planner parameters, and then you get your plans and look at your plans at the back side. Okay, whoops, import catalog. Okay, so I'm going to do, I think I have one here. And I think it's on the desktop. So let's see. Oh, that's not what I want. Rafalski. There's the catalog. Okay, it's thinking about that catalog. It has to try to digest the catalog and try to identify certain columns in the catalog automatically. Okay, it's taking a little bit longer than it does normally. A lot longer than it does normally. Okay, so it's recognized a few of these columns already. There's extra columns in this catalog that I don't need. I do need a magnitude, so I usually use 160, wherever it is. Here it is. This is going to be, no, not that. Okay, and then I do need flux uncertainty. Mag arrow F160W. Okay, and I need a redshift. Z, BPC. This is huge. Let's see, there it is. Redshift. These are just things that I'm going to be able to filter on to derive my candidate sets, as I described before. Okay, and this particular catalog has the 4 columns to allow for the selection of reference stars. So you can see them here, the last 4 columns. It has also a weight column. Okay, I'm just going to call it ref, give it a name. I'm going to select which magnitude I want to work with, and certainty, and specify its mags. Okay, and now I'm going to import it finally. So I'll just do a simple plan because we're running out of time, but just to show you how it works. Okay, from this I'm just going to describe I have to answer a few questions here, but I'm going to describe how to do the filtering. So I'm going to say new candidate set, and it's going to be derived from the parent catalog. And I want to just select redshifts greater than 5, for example. So add filter. It's going to be a magnitude, no, sorry, a redshift filter here. And I'm going to, minimum is 5. I have to click in another window. Okay. Make the candidate set. So this is a child of this catalog here. But I have enough information now to just go ahead and do a simple plan. I don't need a filler list. Fillers are optional, so I'm just going to do a simple plan to show you. This particular catalog is almost the same size as the MSA field of view, but it's rotated by about 45 degrees, so I'm going to give it a rotated angle so it can maximize the coverage of the catalog. And then I'm going to select the specific candidates that I want to observe. Takes a little while to think about the true angle to target, which is needed for velocity aberration calculation. You won't get to set that parameter that's here. It'll just appear, and then won't be editable, I think. Okay, so I'm going to do a 3-shutter slitlet. I'm going to do constrained. I'll just do the entire open shutter area, I guess, but not including the bars. I'd like to nod in the slitlet, so that's going to create 3 exposures. And then I'll do a flexible dither to show you how that works. I'll add a constraint to do a separation from the last pointing greater than or equal to. I'll do 10 arc seconds in the dispersion direction, and I'll leave it available, the entire thing available in spatial direction. Okay, I'm going to add a grading. I need at least 1 for the thing to work. And I'm just going to fake the number of groups and the number of integrations, which there was a description of that already mentioned. And then I am going to select, so this is I'm just going to go with the default centering of the catalog and the area of the catalog to try to select my pointing from, the entire area of the catalog. I'm going to do 10 arc seconds search step size. So this defines the grid cell spacing, basically, in the search grid for optimal pointings. Okay, so at this point, it tells me that I need a multiple of 2 configurations because there's 2 primary dithers. So I'll do 2, and I'll give it a name. This is going to be test, and I'm going to use weights because I'd like to do that. I'm going to generate the plan. Okay, it's done. Okay, so this is all of the pointings. Up here in this box here is just a description of all your planning parameters for this plan. You can select from different plannings from this menu here. And you can see that you have to be scrolled out. I mean, you have to have your window wide enough to see these interior scroll bars so that you can maneuver in here. So I am going to select all the exposures, Command A to do that. And I am going to look at the target results. I'm going to filter my target results. I'm going to see how many primary targets I have in all my exposures. So there's my filtering right there. And now I've got, oh, look at that. So there's 28 targets shown. Those are 28 primary targets that were observed at both dithers. And I have, the majority of them are highly weighted. So I did use weights in this plan. Only one is not of high weight. And this histogram below shows you the number. But let's examine now one of the shutter views of one of the exposures. You click Show. And here's the shutter view. So this is the utilization of the MSA. Again, I said the catalog was only as big as the MSA itself, so there's large areas here that are not utilized. But this is an optimal pointing to observe the targets, the primary targets that I selected. It gets some of, it's one of the pointings that gets most of those targets. And then I want to show you that I can select a target here, for example, and it is highlighted in this view here. Or I can select a set of targets here, and they're highlighted in that view. Or I can click over to the collapsed shutter view, and the same thing, the targets are highlighted in the collapsed shutter view, for example. So that's the kind of maneuverability that you have. That's just a simple plan, but as plans get more complicated, these kind of interconnections actually help you decide which plan is the best. And then when you're done selecting a plan, if this plan is favorable, then what you would do is create an observation from it. You do that at the top here. Select Create Observation. And it describes the gratings that are used in that observation. There's overheads that are listed at the visit level. Let's see, it popped me right over to the visit level, so it's the observation level. This observation only has one visit to do those observations. So it's done the visit breaking already. It only needed one visit to accomplish this science case. And there's where you would normally set your target acquisition parameters, but we do that at the visit level. Because my catalog has these entries already in it, I'm going to get a list of possible bins that I can choose for my reference stars. I'm going to select the one at the top because that's the most favored one. And that has the most sources for, in this case, for that pointing. So that will actually help to choose both the filter and the readout mode for that particular plan, that observation. So once I click and select an item here, it is committed to that visit. I can alternately select other ones, but once you just leave it alone. And if you were to submit the program at this point, it would be committed to use those parameters for TA. Okay, I think that's all I want to show right now.